Hello and welcome back to our series on IGCSE Mathematics. In this video, we'll look at the concepts of reflection, rotation, translation, and enlargement. Based on the subject content of the IGCSE Mathematics Curriculum 0580 displayed on that slide. Let us begin by talking about transformations in mathematics. So, exactly what are transformations? Transformation in mathematics refers to the process of changing the position, size, or orientation of a figure or shape. It's essentially the process of taking a figure and altering it in some way. In our IGCSE Mathematics curriculum, we will be focusing on 4 specific types of transformations. Translation, reflection, rotation, and enlargement. Let's take a closer look at each one of these. In geometry, translation is the process of moving a shape from one place to another without changing its size or orientation. Like how that shape is shifted 9 units to the right and 6 units down without changing its size or orientation. To describe shapes and transformations, we will now use the following language and notation. The original shape is referred to as the object. The transformed shape is referred to as the image. If the vertices of the object are labeled A, B, and C, the image's vertices will then be labeled A', B', and C'. If there is a second transformation, the vertices will be then labeled A', B', and C', and so on.
Excuse me, it seems very simple to translate objects using computer animation, but how can we do it on paper?
Yes, translating objects on paper can seem intimidating, but it's actually not as difficult as you might think. We begin by representing the translation as a column vector, as we learned in part 1 of that chapter, and then proceed as follows. Step 1. Pick one of the original object's vertices and move it in the direction and amount given in the column vector. Step 2. Label the new position of the vertex on the translated shape. Step 3. Repeat steps 1 and 2 for each vertex of the original object. Step 4. Connect the translated vertices to form the image of the translated object. Finally, when asked to describe a translation transformation in a test, you must state that the transformation is a translation and provide the column vector describing the movement. Reflection is a mirror image of a shape that is reflected across a line called the line of reflection. Like the reflected image of that mountain in the water, and here is the line of reflection. In geometry, reflection is the flipping of an object across a line known as the line of reflection, which acts as a mirror and determines how the object will be flipped. The perpendicular distance between a point on the original object and the line of reflection should be the same as the perpendicular distance between the corresponding point on the reflected image and the line of reflection. I believe that solving some problems would make it easier to explain how to reflect shape on a grid. So, let us begin. In this problem, we are supposed to draw the reflection of triangle A using the x-axis as the reflection line. Normally, I begin by labeling the vertices of the shape, such as K, L, and M. The first step should be to draw the reflection line. We will, however, omit that step because the x-axis is the reflection line. The second step is to draw perpendicular lines to the reflection line from each vertex. We'll skip that step as well because the x-axis is the reflection line, and the vertices and perpendicular lines on the reflection line coincide with the grid's y-coordinate lines. The third step is to find the image vertex that corresponds to each vertex on the object shape. Starting with any vertex, for example, vertex K, we will measure the perpendicular distance from the reflected line, which in our case is the x-axis. In this case, vertex K is 2 units away from the x-axis. To find the corresponding image vertex, we simply go 2 units in the opposite direction. This provides us with the image vertex K'. The fourth step is to repeat steps 3 for each vertex of the original object. The fifth step is to connect the reflected image vertices to form the image of the reflected object. Please ensure that you can solve this problem using the same method as before. However, if you have any issues with that, please leave a comment below so that I can provide a detailed solution. Finally, when asked to describe a reflection transformation in a test, you must state that it is a reflection transformation and provide the mathematical equation of the reflection line, as shown in this example.
Excuse me, how can I determine the mathematical equation for the reflection line?
In fact, there are 2 types of problems in which you must determine the mathematical equation of the reflection line. One is simple and the other requires more steps. Let's start with the simple one.
Please pause the video and try to solve the problem on your own before checking the answer.
In part 1 of that question, we can see that triangle A has been flipped onto triangle B, therefore the transformation is a reflection. Again, please make sure to include the name of the transformation in your answer. To find the equation of the reflection line, follow these steps. Step 1. Draw a line segment connecting 2 corresponding vertices on the object shape and the image shape. Step 2. Locate the midpoint of that line segment. Step 3. Draw the reflection line so that it goes through the midpoint and is perpendicular to the line segment that connects the 2 corresponding vertices. In this simple case, the reflection line is parallel to the x-axis and all of its y-coordinates are 1, so its equation is y equals 1. You can follow the same steps to solve the second part of the problem, and you will find the equation of the reflection line to be x equals -1. In the following slide, we will solve a slightly more complex problem.
Please pause the video and try to solve the problem on your own before checking the answer.
It is clear that triangle A has been flipped onto triangle B, therefore the transformation is a reflection. To find the equation of the reflection line, let us repeat the steps from the previous problem. Step 1. Draw a line segment connecting 2 corresponding vertices on the object shape and the image shape. Step 2. Locate the midpoint of that line segment. Step 3. Draw the reflection line so that it goes through the midpoint and is perpendicular to the line segment that connects the 2 corresponding vertices. Verifying the line of reflection with another pair of corresponding vertices is a good way to make sure you haven't made any mistakes. In this simple case, the line equation is obvious from the graph. As we previously discussed, a line equation is an expression that describes the relationship between the x and y values on a line. In this case, we can see that the line has a slope of 1 because the y value increases by 1 unit for every unit increase in the x value moving to the right. Furthermore, at a y value of -2, the line intersects the y-axis. Combining these 2 characteristics, we can write the line's equation as y equals x minus 2. However, if the line equation was not obvious, we should proceed as follows. The first step is to find the midpoint of the line segment that connects the two corresponding vertices. For that, we will use the midpoint formula for the x and y coordinates of the midpoint, in which the x-coordinate is equal to x1 plus x2 divided by 2, and the y-coordinate is equal to y1 plus y2 divided by 2. After plugging the numbers into the formula, we find that the midpoint lies at an x-coordinate of 0.5 and a y-coordinate of minus 1.5. Now we must calculate the slope of the reflective line, but first we must calculate the slope of the line segment using the slope formula, m equal to y2 minus y1 divided by x2 minus x1. After plugging the numbers into the formula, we get a line segment slope m1 is equal to minus 1. Because the reflective line is perpendicular to the line segment between the vertices, its slope m2 will be the negative reciprocal of the slope of the line segment, so m2 is equal to minus 1 divided by m1, then m2 is equal to 1. Using the line formula, y minus y1 divided by x minus x1 is equal to m, we get the line equation to be y equals x minus 2. The problem seems difficult at first glance, but it's really just a combination of the concepts of reflection transformation and coordinate geometry, which we covered in the algebra and graphs section of the course. Please take your time understanding the solution and, if necessary, review the coordinate geometry section. Let us begin by defining the rotation transformation. A rotation is a transformation that turns a figure around a fixed point called the center of rotation, by a certain angle and direction. The figure keeps its size and shape, but its orientation changes. Finally, when asked to describe a rotation transformation in a test, you must state that its name as a rotation transformation. State the angle of rotation. Indicate the rotation direction, either clockwise or anti-clockwise. If the rotational angle is equal to 180 degrees, both directions will arrive at the same position, so the rotation direction is unnecessary in that case. Identify the coordinates of the rotational center. Let's work through that example to see how to rotate a 2D shape on a grid. In fact, tracing paper can be a great tool for drawing rotations, and it's often provided in exams. Let us do the rotation in steps. Step 1. Mark the center of rotation on the coordinate grid. Step 2. Place the tracing paper over the coordinate grid. Step 3. Using a pencil, mark out the center of rotation on the tracing paper and draw a line parallel to the x or y axis starting from the center of rotation. Step 4. Draw the original shape on the tracing paper. Step 5. Place the point of your pencil on the center of rotation. And, while keeping the center fixed, rotate the tracing paper by the desired angle and direction, using the line parallel to the axis as a guideline for the required angle. Step 6. Using the tracing paper as a guide, press firmly on the vertices of the shape to mark them on the coordinate grid. Step 7. Remove the tracing paper and carefully draw the rotated image onto the coordinate grid. It is important to practice that technique to ensure that you can rotate a 2D shape accurately using tracing paper. Place the tracing paper over the coordinate grid. Using a pencil, mark out the center of rotation on the tracing paper and draw a line parallel to the x or y axis starting from the center of rotation. Draw the original shape on the tracing paper. Place the point of your pencil on the center of rotation. And, while keeping the center fixed, rotate the tracing paper by the desired angle and direction, using the line parallel to the axis as a guideline for the required angle. Using the tracing paper as a guide, Press firmly on the vertices of the shape to mark them on the coordinate grid.
Excuse me, how can I determine the rotational center and angle of rotation for a given rotational transformation?
That's a great question, and it's important to understand how the vertices of the shape and its image are related to the center of rotation. When a shape is rotated around its center of rotation, each vertex on the image will move in a circle, with the center of rotation as the center of that circle. As a result, any line segment connecting any two corresponding vertices on the object and the image is a chord on a circle with the center of rotation as the center of that circle. And since the perpendicular bisector of any chord of a circle will pass through the center of that circle. Therefore, to find the center of rotation, we need to find the intersection of the perpendicular bisectors of any two corresponding line segments. Once we have found the center of rotation, we can determine the angle of rotation by measuring the angle between any line segment connecting a vertex on the original shape to the center of rotation and the corresponding line segment connecting its image to the center of rotation. So, to recap, to find the center of rotation of a 2D shape on a grid, we select any two corresponding vertices on the shape and its image. Draw a line segment connecting these two vertices. Construct the perpendicular bisector of this line segment. Repeat steps 1 to 3 with another set of corresponding vertices. The intersection of the two perpendicular bisectors is the center of rotation. To find the angle of rotation, measure the angle between any line segment connecting a vertex on the original shape to the center of rotation and the corresponding line segment connecting its image to the center of rotation. Let us begin with some facts about the enlargement transformation. Enlargement is a transformation that changes the size of a shape. It can make the shape bigger or smaller, depending on the scale factor. When an object is enlarged, the result is a different-sized image that is mathematically similar to the original. With enlargement, the position of a shape will also change. The orientation of the shape will be the same for a positive enlargement. To perform an enlargement, we need to know three things: the center of enlargement, the scale factor, and obviously, the shape to be enlarged. Now, let's look at an example of how to perform an enlargement. Suppose we have a triangle ABC, and we want to enlarge it by a scale factor of 3 with the center of enlargement at point -4 and -5. The enlargement is actually done one vertex at a time. First, we select a vertex on the original object, say vertex C, and measure its horizontal and vertical distances from the enlargement center. As shown in the example here, the horizontal distance of vertex C from the center of enlargement is 1 unit to the right and the vertical distance is 4 units up, so the horizontal and vertical distances of vertex C from the center of enlargement are 1 and 4 units, respectively. To find the horizontal and vertical distance of vertex C' from the center of enlargement, we multiply the horizontal and vertical distance of vertex C from the center of enlargement by the given scale factor. So, to find the vertex C', we move 3 units to the right and 12 units up from the center of the enlargement. After that, we repeat the same procedures for all of the vertices to obtain B' and A', and finally, we draw the new triangle A', B', C', which is an enlarged image of triangle ABC. After finishing an object's enlargement, it's a good idea to double-check your work by making sure the center of enlargement is at the intersection of the lines passing through each of the corresponding vertices in the object and the image. Finally, when asked in a test to describe an enlargement transformation, you must include the transformation name as enlargement transformation. Specify the scale factor. Determine the coordinates of the enlargement center, which can be found at the intersection of the lines passing through each of the objects and images' corresponding vertices.
How do I enlarge a shape if its scale factor is negative?
Actually, the procedure is very similar to that used for an enlargement with a positive scale factor. The main idea is to account for the negative sign when multiplying the scale factor with the horizontal and vertical distance between the vertices on the object and the center of enlargement, when calculating the position of the image vertices with respect to the center of enlargement. Let's run through that example to ensure you fully understand the steps involved. The enlargement center is at -1 and -2. The scale factor is -2. And the shape is the triangle ABC. Let us write down the horizontal and vertical distance between the vertices on the object and the center of enlargement. Vertex A will be -3 and -2, as we moved 3 units to the left and 2 units down. Vertex B will be -1 and -2. Vertex C will be -3 and -4. Multiplying by the -2 scale factor we get. Vertex A' will be 6 and 4. Vertex B' will be 2 and 4. Vertex C' will be 6 and 8. Let us plot the image vertices. Vertex A' will be 6 and 4. Vertex B' will be 2 and 4. Vertex C' will be 6 and 8. Let us plot the image vertices. It is now clear that the object's orientation has changed because a negative enlargement rotates it by 180 degrees.
Congratulations, you've made it to the end of Chapter E7, Vectors and Transformations in the Cambridge IGCSE Mathematics Extended Curriculum 0580, designed for the 2023 and 2024 exams. But don't stop here. The next exciting chapter is E8, Probability. Whether you're new to the subject or looking to expand your knowledge, this chapter will help you develop a deep understanding of the fascinating world of probability. So keep on learning and join us in Chapter E8. We look forward to seeing you there.
Goodbye.